Okay. So let's start off with pyramids. Let's review sort of the anatomy of a pyramid. Let's why don't you put all the bones and all that stuff away. So pyramids are pyramids are built from they're polyhedrons, right? They're built from a bunch of polygons kind of pieced together. They consist of a base, and then they're gonna have triangular faces that all meet at a common vertex. Okay? If this is in this case, the vertex is not lined up over the center of the base. Usually for regular we'll deal with regular pyramids, and it will. They'll end up with the vertex being right over the center of the base, but it doesn't have to be that way. The formulas stay the same. So we would say that the base is what sits on the coffee table, so to speak. The lateral faces are going to be the triangular pieces of the pyramid. The lateral edges are going to be where the triangles meet, right? The base edges are just going to be the parts that are the edges that are in contact with the glass coffee table. And I think we got them all. Yep. Okay, the altitude is the height that the vertex is above the coffee table. So in other words, it's the perpendicular distance from the vertex to the base. Okay. Also, we call that the height. Okay. So there's the height. You can see that it meets, in this case, we've got a regular polygon for the base. This is a regular pyramid where the vertex is right over the exact center of the base. The slant height is different than the length of a lateral edge. It's not the same thing. A lateral edge, this is a lateral edge right there, right? The slant height is the perpendicular distance from one of the base edges to the vertex. Let me say that again. The slant height is the perpendicular distance between one of the bases, or the base edges, and the vertex. Okay, so that has to be a right angle. So it's on one of the lateral faces. Yeah. And for a regular pyramid, all the faces are going to be congruent, and so the slant height will be the same for all of them. And so when we talk about the slant height for a regular pyramid, it's just one number, right? Does that make sense? Okay. All right. Okay, so what if we want to do something like, well, I'm going to skip that. Okay, so what if we need to calculate a slant height? We can do that. Like if we knew, for example, what one of the lengths of the base edges was, how is the slant height going to be related to that? Okay, and let's take, for example, we're going to specifically talk about a square pyramid here. By a square pyramid, what do you think the square part comes in? The base, yeah. So when we talk about a pyramid like a hexagonal pyramid or a square pyramid or a pentagonal pyramid, we're talking about the base because all of the faces are going to be triangles, right? Yes, sir.
Oh, I was looking at the
Okay, so what's the answer?
one.
So if S is the length of one of the base edges, what's the length of how is the slant height going to be related to that?
Oh, do we have the bottom and then the inside and the
Okay, so we can set up a right triangle, which is always a good idea, because if we can set up a right triangle, that gives us a relationship between all three sides, the Pythagorean theorem, right? And so the bottom edge down here, the bottom edge, or the bottom side of the bottom leg of that right triangle is just going to be half of the length of one of the edges of the square base, right? Because this, after all, on the bottom, the base that's sitting on the coffee table is square, right? And so the center of that square is going to be a distance of half of the length of one of the sides of the square from any edge, right? Okay. we already said that the altitude or the height is the distance from the vertex down, the perpendicular distance from the vertex down to the base. And notice that this is a right angle, right? Okay, and so then all we have to do, and those are parameters that we would know that would describe the whole pyramid. We would probably know the height, and we would know maybe the width of one of the base edges. So now all we have to do is just apply the Pythagorean theorem, and we can solve for the slant height. Okay, so it's just going to be the square root of this distance, which is 1/2 s squared, plus this distance, which is h squared. Okay, that helps us out. So then we know the slant height. Okay, why is that so useful? Well, we're going to see. So let's shift gears and let's look at a regular hexagonal pyramid. So now the base is a regular hexagon, right? And all of the lateral faces are going to be congruent triangles once again. And let's see if we can come up with a surface area on this. Well, if we unfold this like a net, remember dealing with nets?
Yeah.
We've dealt with this before, right? So if we were to cut along all of the lateral edges and unfold the thing, it would just look like this on there. So then we want to add this thing up, we've really just got two different kinds of areas that we're going to add up. We've got the hexagon that makes up the base, right? Plus 6 of these congruent triangles, right? Okay, so we could even say if we want to, that if we want to relate these in some way, if we say that little b is going to be the length of one of the base edges, if this is a hexagon, then the perimeter of the hexagon must be 6b. Do you agree? Okay, all right. So let's see if, I think they messed this up a little bit. They did. Well, I'll fix it. So we know that the total surface area is just the area of the base plus 6 times the area of one of the triangular lateral faces. So what is the area of a triangular lateral face? Well, if we go back, we said that the base edge was b, right? And the slant height we're going to call L. We go back real quick. So we're saying, everybody see that this is the slant height right here. If I draw this segment on the pyramid, it would be like maybe right there, right? So that's L. Okay. Now it's there. Okay. So if we want to add up the area of one of those triangles, it's going to be half b times L, half the base times the height, right? The slant height of the pyramid becomes the height of one of the triangular faces if I cut it out and set it on the table, right? Okay. So then we could say that the area of a lateral face is just 1/2 BL, and so we get B, which is the area of the face, which we'll have to calculate separately, plus 6 of those. Well, they forgot to do something here. This 1/2, I could just factor that out front. Oops, so there's a 1/2 there. And we said that 6 times B, 6 times the length of a base edge, is just the perimeter around the base, right? So we could replace this part right here with a capital P for perimeter. Okay? And that ends up being our easiest way that we can write the formula for the surface area of a pyramid is the area of the base plus 1/2 times the perimeter of the base times the slant height. Okay? So let's try that. So what about something like this? Let's see. Yeah, let's try this guy. Let's try this guy. And we haven't talked about a pocket yet. We may go back and get that. But we don't really need to. We can calculate the area of hexagon just by breaking it up into triangles before we need to. And I'll give you or you could do, there's a bunch of ways you could do it. But probably the easiest way is just to break it up into 6 equilateral triangles. And we'll get there. We can deal with that. But let's see if we can get the lateral area. The lateral area is just going to be the combined area of all the faces of the pyramid. Okay, so based on these measurements up here, we know that the area, the the surface area is the base plus, what was the rest of it, you remember? 1/2 times the perimeter, times the slant, perimeter of the base times the slant height. Okay, so based on this pyramid here, what's the perimeter of the base gonna be? Yeah, 6 times 6. Okay, so we know P equals 36, and the units will just be meters. I'm not gonna write the units down. Okay, what about the slant height? They give us the slant height, don't they? It's 8. Okay, so then we can calculate the lateral area is just 1/2 times 36 times 8, whatever that is. Right? No big deal. Okay, what about the area of the base though? Let's focus on that. How are we going to get the area of the base? There is a formula for this, but you'll just forget it anyway. I know I do. I would just figure it out for myself every time. Yes, sir.
Would it be 12 plus 6? Not 12.
So by the 6 triangles, so then we
Yeah.
do 6 times the height, and then we'll divide it by 2.
Okay, there's a way, no, not Google it. There's a way we can do this. Let's focus on this right triangle right there, how about? Everybody see that right triangle? Okay, so what's gonna be the, let's call this the base. I'll tell you what, let's do, let's make this right triangle so it lines up just a little bit better. Let's do our right triangle right here. How's that? So what's the length of the base? 3, okay. Now, we haven't reviewed this stuff this year, but do you remember talking about special triangles in the past, 30, 60, 90s, and 45, 45, 90s?
30, 60, 90, which is like half of an equilateral triangle, and then it's 3, 4, 5, which is
Okay, you could either take that shortcut, or we could do something else. Think about what's this angle gonna be right here? And why? No. What's it gonna be? Katie, what's that angle gonna be right there? If I wanna look at this angle, does
60.
that make sense? Okay, how come?
Because I know hexagon.
Okay, so what if we just look at the hexagon in general? You remember the formula for calculating the sum of all the interior angles? What was that?
The side minus 2.
Okay, n minus 2 times 180, right? Good. And that, remember where that comes from. One way that we can always get that is by just saying, if I start at a vertex, this is good review. If I start there, I could, from that vertex, I could create 1, 2, 3, 4 triangles, right? Because all of the non-consecutive vertices, or non-adjacent vertices, I would create a triangle with, right? Does that make sense? And so then each of those has 180. But, or just remember the formula. So we know that 6 minus 2 is 4 times 180 is 720, right? So we have 720 degrees of, if I add up the sum of all the interior angles, but they're all congruent because it's a regular hexagon. So how would I find out how big this angle is right here, for example? Divide by 6, right? I have 720 degrees to go all the way around, divided by 6 is 120. Okay, so if that big angle is 120, well, isn't that true? Aren't those angles right there congruent,
Yeah.
right? Because they're connecting to the center, right? So then that must be 60, right?
Yeah.
Okay, so if that's 60, then let's go up here. There's a lot of really cool geometry. So if that's 60, let's look at another one of these triangles, but this time let's look at one of those triangles. If that's 60, well, that's obviously 60, right? Same relationship. So what's that?
60.
60. What kind of triangle is that?
Equilateral.
It's equiangular and equilateral, right? So then what is, you can tell me now, what is the length of that hypotenuse in our orange triangle? What's it gonna be? 6. So if that's 6 and that's 3, we could solve for that distance by just using the Pythagorean theorem, couldn't we? You get that?
Yeah.
Okay. So we could say if we call it x, then we're just gonna say that x squared plus 3 squared
Equals 6 squared.
6 squared, good. So x squared equals 9, x squared plus 9 equals 36. So x squared equals 27, right?
Yeah, that's right.
And so x equals the square root of 27, which is just 3 radical 3. Square root of 9 times the square root of 3, right? So there we go, okay? So we found that. If we find that distance, that's 3 times the square root of 3, then we now know how to calculate the area of this little triangle, but also this one, right? We could even do the big triangles now. Everybody agree? Because isn't that just the height? If we look at this pink triangle here, isn't this really, if we call this the base, right? Isn't this just the height then? Right? And so the area, I'll make it a pink A for the area of a pink triangle, just equals 1/2 times the base, which is going to be 6, right? That whole distance is 6. 1/2 the base times the height, which is, we're running out of colors here. The height is 3 times the square root of 3, right? And so I get 1/2 times 6 times 3 times the square root of 3, which is what, 9 times the square root of 3? Yep.
What's the actual formula for the area of hexagon?
Of a hexagon, it is,
So the area's
I'll tell you here in a second. I'll tell you what, I can't remember off the top of my
Gotta
head
guess on
though.
what it is.
What's that?
Gotta guess on what it is.
You got to guess on what it is?
Yeah.
What do you think it is?
Like, if we call the distance between the widest distance it can be, W, and then you add all the bases, and times that by the half of by the distance to the center of it, you should end up with the area.
That might be right. That might be. That's not the way it's traditionally written, but I can see, I think you're right, if I follow you.
And then if we multiply that area by 6, then we get the area of the whole.
Right, okay, so the pink area then, boy, it's getting really messy here. I'm going to finish up right here. So the pink area, the area of one of the triangles, is just this, right? Which is 3 times 3 times the square root of 3.
Which is,
So the area of the whole base is just 6 of those, right? So that's just going to be, what, 54 times the square root of 3? Okay, make sense? So there's the area of that hexagon. Now I'm going to tell you what the,
Wait,
if I can remember.
6 times 9 multiplied the square root of 3.
Say it again.
So you distributed, right? So then it's 6 times 9, but then it's also 6 times the square root of 3.
No, because, okay, so what's 2 times 3 times 4?
24.
Okay, it's not 48, is it?
No.
So I wouldn't multiply the 2 times the 3 and the 2 times the 4.
Oh, yeah.
I multiply things in pairs, right? Okay. So 54 radical 3, and then we already figured out, what would we say that what we end up with here for our lateral area? It was 1/2 times 36, which is 18 times 8, which is 144, is that right? 121, is that right? 18 times 8, yeah, 144, that's it. So we get this plus, so our final answer, to get rid of all this junk. So our final answer then is just going to be, what 54 radical 3 plus 144. That's an ugly number, but it's just a number, right? But it's an exact number too.
Can't add the everywhere.
Nope, you can't, because radicals are treated like variables, right? We can only add up like terms. Like if I had x's and y's, I couldn't add up x's and y's, but I could add up x terms, right?
So 50, it's
Yeah.
basically like 54x.
So you always just treat radicals like variables when you're combining like terms. We'll get to that next year. That make sense? Okay. I will give you, and so by the way, for a regular polygon, this is the formula that we skipped, that I'm okay with you using. It's fine. The area of any regular polygon is 1/2 times the apothem times the perimeter. And what's the apothem? The apothem is just the perpendicular distance from one of the edges to the center. In other words, it connects the midpoint of an edge to the center. So in some problems that might be given to you. And if it's given to you, you can just use that formula. Although if that was given to you, wouldn't it have been pretty easy to find the area of the base just by adding up triangles? The hardest part of that whole process was finding that distance anyway, right? So it's not that big of a thing. Okay? There's a lot of good geometry. Okay, so there was our answer. 54 radical 3 plus 144, roughly 237.5. Okay, so then how does this relate to a cone? Well, a cone's really similar. Now let's think about this. You gotta really, I would do this for any geometry class, but for you guys, I want to see if you can take the conversation we had yesterday and sort of extrapolate that conversation into this conversation, merge the two, and see if you can come up with the appropriate formula. So we said that the surface area of a pyramid was equal to the base plus 1/2 times the perimeter times the slant height, right? Okay. So in this case, the area of the base is easy. That's just a circle, right?
Yeah.
Okay. Think about this now. How are we going to deal with the 1/2 times the perimeter and the slant height business?
It'd be 1/3.
Say it again.
Find it as a cylinder.
Okay, so now, what did we say? How do we get from a pyramid to a cone?
That's the base size approach.
Okay, so it's just going to be, all it is, it's just like effectively, it's like an regular infinigon pyramid, right? As the number of base, as the number of lateral faces goes to infinity, it's going to smooth out that angular nature, right? And the polygon is going to become a circle, right? And so then the slant height, what does the slant height become? The slant height was the lateral distance from, or the perpendicular distance from one of the base edges to the vertex. Well, now the base edges have just all converged to become a circle.
Anywhere, any point on
So it's any point on the circle, yeah. And it's what we call the slant height of a cone, is just literally the linear distance from a point on the circular base to the vertex, right? Okay, so it means kind of the same thing. Yes?
I think we're gonna be solving this on.
Maybe, it's possible. Okay, and so then,
You can do it.
what is this gonna become then? What's the area of a circle? Okay, just pi. We don't wanna say, now, okay, let me say something about that. I know you guys in the past have always used, because I wrote a lot of these problems for the middle school curriculum, they always wanna use 3.14 as pi. Is 3.14 pi? No, it's not. What is pi? The pi button. Pi is the symbol pi, right? So no more 3.14s. Listen, please.
Pi is the square.
So then what is the area of a circle in terms of pi? Pi r squared. So now we can take the base, and that's going to get converted into pi r squared. What about 1/2 times the perimeter times the slant height? Well, what's the perimeter of a circle?
That's our circumference.
It's the same thing as circumference. In fact, we call the perimeter of a circle the circumference. 2 pi r, right? So this becomes 1/2 times 2 pi r times L. The 1/2 and the 2 cancel, and what do you know? Voila.
Pi squared.
This is, this is our, right here. Here's the surface area of a cone. Base area plus lateral area. Pi r squared plus pi r L, where L is the slant height. Okay? Makes sense. More importantly, you see how you get from the pyramid to the cone, right? They're strongly related.
Okay, why didn't they build cones instead of pyramids?
I think, yeah, I don't know.
Because they like ice cream too darn much.
All right, so Try this. How would we do this here? Math.
So we have the formula.
Yeah, I mean, really, that, when you probably don't even need to, it's just plugging in, right? Plugging in, chugging. Pi r squared, so pi times 4 squared, plus pi rl, right? So pi times 4 times 6, and that's it. That's it. Good deal. Okay. All right. Okay, so we're done with this one. Put that one away. Oops. All right, here we go. Okay, so take a look real quick. So we looked at these a little bit yesterday. Prisms. Remember, prisms are just polyhedrons that have two congruent faces, called bases. Okay, so in this case, but okay, they can't just be two congruent faces. They have to be, okay, why is this, draw a picture. Okay, so would you agree, my pictures, I'm not much of an artist, so my picture's not going to be great, but here's the idea, right? So
Billy gets to talk about that.
okay, you get the idea?
That is a beautiful painting.
Well, it's not so great, but there's my hexagonal prism, right? So would you agree that these are the bases down here? Right? Those are the bases? No, they are the bases. Those have to be the bases. Okay. Why couldn't, I want you to tell me here, why couldn't these be bases? Why couldn't that rectangle and this rectangle be bases? 'Cause what if I took this thing, now just imagine, so I've got this prism sitting on the coffee table like this, and I'm just going to pick it up and set it down on one of its lateral faces. They're congruent.
Then
They're-
wouldn't the sides not all be the same shape?
Ah, okay, good, because then if we do that, the lateral faces aren't all the same, right? So you see the difference? We can't just say, so when the book says that they just have to be congruent, that's not enough. It's not enough. They have to be congruent, but then all the other faces have to be congruent also. Does that make sense? Okay. So is there a case where we could do that? Where we could take our object off the coffee table and set it down this way and still have it work? Cube would work, wouldn't it?
Or a triangular prism.
Or a regular tetrahedron. Yeah. Okay, that would work. Okay, but that's actually no, that wouldn't work. Wouldn't work. Would it? Only one would be a cube. Strike that. Okay, so the anatomy of a prism. We've got the bases, very similar to a pyramid. We've got the lateral faces. This time, though, the lateral faces aren't triangles. They're what? Rectangles. Rectangles. Good. We got the lateral edges. Okay, we got the height, just like before. Okay, this is an easier one to deal with. Now we can do some weird kinds of prisms also, called oblique prisms, which are just like we took a regular regular prism, and we just pushed it over to the side. And ironically, if we do this, the same formulas are going to work for calculating surface or at least for calculating volume, okay? But we'll deal with that later. So, what do you think? This is going to be an easy one to do, very easy surface area. If I take a prism and I form a net out of it, so I cut it, pretend it's made of paper, and I cut it along the edges and I lay it out. In this case, we've got a regular hexagonal prism, right? Okay? So that gives me 2 hexagonal bases and 6 rectangular edges. Well, what's easier to find the area of, a rectangle or a triangle? Rectangle. This is easy, right? This is not a big deal. So, make a prediction for me. What is the surface area of this animal going to look like?
A rectangle and then
So, S equals how many bases?
2D.
2. Okay. Plus, now let's look at these. Let's look at these individual rectangular lateral faces. Let's say that each one of those, just like before, let's call this distance little b, okay, and let's call this distance the height. All right. So what's going to be the area of one of those individual rectangles? Little b times h, right? So we're going to have to do 6 of those. Okay, but what would 6 times b equal? What would 6 times b equal? If that's b. P, right, good. It'd be the perimeter. So we could rewrite this then, just like before, as 2b plus ph. That's it. How simple is that? That's the formula for the surface area of a prism. Right? You have the 2 lids, the 2 bases, plus the perimeter of the base times the height, and that's it. Okay? Make sense? All right. When are we out of here? 20, okay. Okay, so then, let's just jump up to that spot. Oops. So there's our formula, right? Now I want you to do what we did last time. There's the formula for a prism. Let's make the jump from a prism to a cylinder, right? A cylinder is just a prism with how many sides? Infinite, right? You know what I'm saying? Infinite sides. So then the bases, what does the area of the base become if these are circular all of a sudden?
2 pi r squared.
Okay, so pi r squared. So we end up with. Whoops. Okay, so we got 2 bases. The perimeter of a circle is just circumference, right? So that becomes 2 pi r times the height, and that's my answer. I just get 2 pi r squared plus 2 pi r h. Okay, that's it. Make sense? Yes. Close. Yeah, we're about done. Okay, there's one other. I like this way. I like this way of doing it. Imagine though, there's another way to get that 2 pi r h. I really like this method of doing it. So sure, we were able to come at that from the perspective of converting a prism to a cylinder, but we don't even really have to do that. We could find by adding up the pieces here, we could get directly to the surface area of a cylinder. Obviously the bases are circular, so we get 2 pi r squared. But what about the lateral area? Yeah, imagine that it's like say you got an oatmeal, like what do you call that? Oatmeal carton. And you take the bottom and the top off, and then you just cut up the side, and you unfold it, right? It becomes a rectangle. So if I unfold it, yeah.
So you could times the height by the circumference?
Okay, so if we do that, would you agree that this distance right here, if I unfold this thing, so this red distance,
The width? Oh, no, that's.
right, that ends up being width of the rectangle we get if we unfold it, right? The height is just h, right? So we end up with h times, well, that's the circumference of the circle, right?
Yeah.
Make sense?
Well, it's not really a cylinder, it doesn't have a top or bottom.
Okay, but we took the top and the bottom off, right? Here's our oatmeal container. We cut out the top and the bottom, and there they are. Each of them has an area of pi r squared. Then we cut straight up the side and unfold it.